So next we are going to talk about something different called the chemical potential. And this is very interesting. Okay, so far, what we have done is that we have considered systems where, the independent variables are really energy and the volume, right? So what we did is that we took one system and connected to another system, and this was either it was a diathermal wall, or we connected them in a way which where there was a diathermal wall, but this wall was movable, right? So in that case, the volume could change. So this was like movable slash and or diathermal. But in both cases, our walls were impermeable. So that means that, the particles here could not escape here and vice versa. And the particle here could not escape here. So that means that the particles on both sides, N1 and N2, they remained constant separately, right? Now what we can do is that we can even remove that constraint. And if you remove that constraint, then the particles can be exchanged. In that case, the entropy of the system is no longer just a function of E and V, but it will now become a function of the number of particles. So it'll be KB log of omega EVN, right? So this is just as we did in the previous cases, but now we're including an independence. Now, if I just as before, if I ask for a equilibrium condition, we are going to get that the temperature of the two systems, which was defined by del S by del E, the temperature of the two systems are the same. And that has to do with the fact that we have the E dependence. And then we also have, because of the V dependence, that the pressure of the two systems also have to be the same. And the pressure was defined by T times del S del V. But now we also have an N dependence. And if we go through the same derivation as before, what we will see is that not only do we require T1 equals to T2 between the two systems and P1 is equals to P2, we will also require mu1 is equal to mu2, where mu is given by minus T del S by del N. Of course, because N is such a large number, we can consider this to be a continuous variable. Okay, so this object, mu, is called the chemical potential. And so the idea is that the chemical potential is the quantity that has to be equal between two systems for it to be in equilibrium with each other. So, essentially now E, the energy of the system, or let's not E, the S, right? S is now a function not just of E and V, but also of N. So if I now compute del S, there'll just be one extra term. And, and what we can do is that we can rearrange it and write this as dE is T of ds minus P dV plus mu dN, right? Where this mu is the chemical potential. Okay, so the definition of mu is this, but from this equation, we find that mu can also be expressed as the partial derivative of E with respect to N, keeping the volume and entropy constant. So what does this mean? This means that mu is, the chemical potential is the energy that is needed to increase the particle number by 1 unit. Okay. Number by 1. But keeping the volume and the entropy the same. Okay, so now we have two expressions for mu. One is the expression that we used to define mu. Another expression is from the quote-unquote first law, not quote-unquote, it is the first law, and that's del E by del N, keeping V and S constant. And how do we reconcile this? So how are these two related? Well, recall that we had an identity for a function of two variables. So if we had a function x, which was a variable of y and z, that we could write del x, del y, but keeping z constant, and then del y, del z, keeping x constant, and then del z, del x, keeping y constant. All of this was -1. Now what we can do is that we can take E, which is a function of entropy, V and N. So I'm just inverting the expression. Instead of S being a function of E, V, and N, I'm writing E as a function of S, V, and N. And what we can do is that we can fix V. V is fixed. So V is fixed, then E is just a function of S and N, right? So, and you can think of it the other way too. You can think of S as a function of E, V, and N, and you're fixing V. So if I do this, then I can write the analog of that of this identity, where we have del E, del S, but now we are keeping V and N constant. And then del S, del N, we are keeping V and E constant, right? And then del N by del E, we are keeping V and S constant. And that has to be equal to -1. So let's see if this is true. So what is the left-hand side? The left-hand side is, this thing is nothing but 1 over the temperature. And this thing is the definition of the chemical potential, and therefore we get -1 over T times mu. And this thing is del N by del E, where V and S is constant. And this left-hand side has to be equal to -1, which is the right-hand side, which gives us the expression that delta E, so here delta E, delta N, Vs is equal to mu, okay? Okay, any questions?
Sir, yes.
Yes.
So does this have anything to do with the bonding energy of atoms? Is that what the E stands for in the chemical potential?
The mu.
the E in the mu equation.
Right.
E is the internal energy.
Internal energy.
Yeah.
I was just asking if this U thing has anything to do with the bonding energy of atoms, like the bond energy. Hello.
Yeah. No, I'm thinking.
Oh.
I think it has more to do with the potentials that you hear about during osmosis and diffusion. It's more to do with those.
Well, bond energy is type of potential energy too, right? The
Yeah.
chemical.
No, I mean, so for example, if I have, yeah, I think it can, but you have to take into account that when we're talking about binding energy, we are also talking about a phase transition of your material.
Yeah.
So that's something which is so far I haven't really gone into, so it's a little bit outside the scope of this course.
Yeah. It goes into chemistry, I guess.
Yeah, I guess it goes to chemistry, and the statistical mechanics of chemistry is related to what is known as phase transitions. Well, part of it at least. So yeah, I'm not exactly sure. Let me get back to you on that. Okay.
Sir,
Yes.
shouldn't d by ds be t and not 1 by t?
ds, which one?
dE by ds.
dE by ds is t. I think you're right.
Because they're canceling out.
The dimensions doesn't match otherwise.
Yeah. So So this is you're saying this is t. Yeah, you're right. Yeah, of course. Because then it cancels out this one, right? Yeah. Sorry about that. Yeah. All right. So I think Oishik, you're here, right?
Yes, sir. But sorry, I was a bit late.
No, it's okay. I just want to make it's a good time to do another round. Moon, are you here? No. Okay. And Mihdat?
Yes, sir.
Okay, good. And Sitima?
Sorry, I couldn't catch up, so I think you're breaking up.
Okay, you're here. Acha, theek hai, sir.
Oh.
Muhammad Abdullah?
Yes, sir.
Okay, good. Nahi, you're here, right? Yeah.
Yes, sir.
Good. Awesome. All right, so yeah, let's move on.